Okay, today we're going to talk about, for a little bit longer, the properties of light. You'll see. So, the technical term for light is electromagnetic waves. Okay? So, light is just kind of I don't know, it's more of a nickname, really. Electromagnetic waves are different than most of the types of waves that we think about because water waves or sound waves have to have a medium to travel through. Okay? If you go out into space, you can take the biggest pair of crash cymbals you want and slam them together. They're not going to make any noise because there's no air to vibrate. So, I don't know, the tagline from Alien in, I think it was 1979 when it came out, was, "In space, nobody can hear you scream." And that's true because there's no actual air there to make sound. So as much as I like Star Wars, they're actually pretty terrible movies as far as physics go because, you know, any of those explosions and stuff, you would not hear anything.
Well, it's in a land far, far away, so it could be different.
No, the physics should be the same. So a better I don't know, representation of how sound actually works in space is actually the series Firefly. Anybody ever seen Firefly? Know anything about it? Okay. Anyway, in that series, anytime they do an exterior shot of the ship that's in space, they don't even play any music. There's like total silence. Okay, you can leave now. Now get out. Get out! Just kidding. Yeah, that's because you weren't paying attention, so you didn't know that I was joking. Firefly is an amazing show, and I'll have you stop talking right now. So, no, we are not doing that. Okay, listen. Electromagnetic waves, though, they can go through anything. I mean, they just we say they're self-propagating. They can go on their own. So here's a diagram that sort of shows how we think of electromagnetic waves. Okay? The orange here represents the electric field, and the purple represents the magnetic field. What's cool about when you learn about the electricity side of physics is that if you take an electric charge and you vibrate it, it actually creates a magnetic field. So in this self-propagating wave, what happens is that as the electric field rolls along, it kind of pulls a magnetic field with it, and that's going to pull an electric field that pulls a magnetic field. And so these things kind of go on their own. So electromagnetic waves don't have to have a medium to travel through. Okay, they can go through space. That's how light gets here from the sun. That's how radio waves can be used to communicate with satellites and things like that. It's all through electromagnetic waves. Okay? And here they're showing a wavelength. So between two similar parts of the wave, we have that symbol lambda to stand for a wavelength. Now, yesterday we introduced the different types of electromagnetic waves, or light. Right? That's where we were right there. I lost my way here. Here we go. This is what I want to look at. This chart sort of shows about the size of each of these electromagnetic waves. Okay? So right here, we're going to start down here. We have radio waves. So the size of the wavelength of radio waves goes from about the size of a soccer field to about the size of a baseball. Okay? So as far as how long is it between waves, for radio waves, it's in that range. Soccer field to a baseball, something like that. Okay, down here they show the frequency, so you can kind of see that in hertz. But now radio waves are used for, obviously sending radio signals. They don't have, here they have radar. Most types of radar nowadays do use microwaves, but there are types that use radio waves. That's where the name radar comes from. Okay, FM radio is going to be higher on the frequency spectrum than the AM radio. Okay, and then we get into microwaves. So microwaves, we always think of a microwave oven because that's the common thing that we use. But your cell phones all emit microwaves, all of them. That's how they communicate with the towers. So when you send a text or whatever, that information is being sent out through microwaves. It goes to the tower, makes contact, and then the information is sent out from them. When you get a text back, you're receiving those microwaves back, and the cell phone figures those out. Microwaves, as far as their size, are from that baseball, kind of where the radio waves left off, down to about the size of a period. So the smallest microwaves are going to be maybe a little bit smaller than a period on your paper. Of course, they're all traveling very quickly at the speed of light, but their actual size is fairly big. We call them micro because, micro means small, but really they're one of the biggest ones other than radio waves. Okay. Infrared, we talked about yesterday, is, we think of as heat. So here they've got one of the sources of infrared is people. Okay, one of those cameras that reads infrared, it can look on you and see, where the warmer spots are because you are giving off electromagnetic waves. So all of you are electromagnetic wave emitters just because you're at a certain temperature. So infrared waves can be read to read temperature. And they're going to be about the size of a cell down to about the size of a bacteria. Okay, the next one is visible light, of course, given off by a light bulb or the sun. And visible light is actually a fairly narrow range. Of all the electromagnetic waves, our eyes are only attuned to a very small portion of the electromagnetic spectrum. Okay? The things that we look at that, we think of have certain properties, it all has to do with the types of waves that our eyes pick up. The reason why this wall looks opaque, we can't see through it, but you look through glass and it looks transparent, is just because our eyes are going to absorb visible light. If we saw in, let's say, microwaves, then this wall would look transparent as glass. We'd be able to see right through it, but our eyes can't pick up microwaves. If we saw in UV, we wouldn't be able to see through the glass window because UV can't go through glass. Yes?
Do we have machines that can see radio waves and microwaves?
Yeah, so a radio antenna is basically a machine that can see radio waves. I mean, well, it's not something that you can just hook into your brain so that you can see in that way. But when you look at any pictures from space, what you are seeing is actually a bunch of pictures put together using data from radio waves, microwaves, all those sorts of things. So we do have computers that will read the radio waves that are bounced off or given off from an object and turn those into pictures. We just then, we're seeing the visible display of what that looks like. Okay. Visible light is, kind of down between that bacteria and virus. We go a little bit higher, we get UV. Of course, we think of UV given off by the sun. What's interesting is that these lights right here actually give off a bunch of UV and X-rays where the reaction actually produces the energy, but those UV and X-rays run into a coating around the outside of the glass, and that will actually fluoresce and give off the visible light. If you make a bulb that doesn't have that coating on it, you don't see visible light coming out, but you can use it to make certain things fluoresce. So if you've ever seen a black light is basically a fluorescent light without the coating. And the UV that's given off will hit certain objects and make them glow, so like things that are white or bodily fluids, that kind of stuff. So crime scene investigators will use that sometimes to see, there was a big blood splatter here that's been cleaned up, because it's going to fluoresce when it's hit with those UV rays. Okay, up from ultraviolet, we talked about X-rays. Okay, we don't have a lot of natural sources of X-rays, although there are some, like the sun gives off some. There are some things in space that will give off a lot of X-rays, but for the most part, X-rays are produced, in machines here on Earth. And then we have gamma rays, and gamma rays are produced by some types of nuclear radiation. Okay, and also certain types of things that happen in space, like supernova, and those get very small. So X-rays and gamma rays are smaller. The wavelength is smaller than a water molecule. Okay. Now I'm going to introduce a term here that will be important to know. Okay, we have this term, ionizing radiation. Ionizing radiation is any type of electromagnetic radiation that has enough energy to knock electrons out of atoms. Now, I want to talk about that term radiation because that's a charged term. Radiation is not the same as radioactivity. Right now, you guys are giving off infrared radiation. Radiation just means energy that spreads out. Okay? The sun gives off visible light radiation. Okay? Your cell phone is giving off microwave radiation. Radiation is just any type of electromagnetic wave that spreads out. Radio towers give off radio wave radiation. Okay? But we want to distinguish what types of radiation are ionizing. The reason why we hear this term and why it's important is because if we have radiation that can knock electrons out, that is able to actually damage things. So when we worry about cancer risks from radiation and that kind of stuff, we want to look at what types of radiation actually can knock electrons out, because that'll can screw up the cell. If it screws up the right part of the cell, it could cause a cancerous cell. When we look at the electromagnetic spectrum right here, ionizing radiation tends to fit in about right here. Okay, not all UV is ionizing. A lot of it is. But then X-rays and gamma rays. So, have you ever had anybody tell you that cell phones give you cancer? That you shouldn't, put it in, guys shouldn't put it in their front pocket because it'll make them sterile or something like that? Yeah, that's dumb. So, yeah, that too. Yeah, all of that. Bluetooth works through microwaves too. So, all of those things, right, use microwaves to communicate. And microwaves, as we can see, are quite a ways away from the types of ionizing radiation. The farther you are up this chart, the more energy the waves are going to have. We can see heat from a campfire has more energy than microwaves do. Okay? Visible light has more energy. You have more of a chance of getting cancer standing here having visible light shown on you than you do from your cell phone. Okay? The waves that are given off just don't have enough energy to knock any electrons out. Now, you do have to be careful of these types of radiation. That's why you should limit your sun exposure. Now, some sun exposure is important. UV actually does stimulate the production of vitamin D3 in your skin. So, you know, it's not like you should hide in your basement all the time. Okay? Right, Braden? Weird. But too much UV does increase your risk of certain types of skin cancer. When you get sunburnt, that is from UV radiation destroying enough cells to actually give you a burn. I mean, it's the same basic result as putting your skin near a hot fire on a hot burner. It's just you've done it with UV instead of the heat from the burner or whatever. You've killed cells. Okay. X-rays have more energy, so they're more likely to ionize cells. So that's why when you go to the dentist or whatever, they're going to cover up your soft bits, your internal organs, with a lead-lined, apron to try to limit your exposure. Now, here's the thing, okay? Taking a plane ride actually exposes you to more X-rays than getting a picture of your teeth or whatever. You shouldn't have like 100 X-rays done every year. That would be a lot. That would increase your chances. But a couple X-rays here or there is not going to increase the likelihood of getting cancer all that much. Okay? And it has actually been shown that people that, like business people that fly a lot, actually do have increased rates of cancer compared to people that don't. And that's because the atmosphere actually soaks up some of the X-rays and the gamma rays from the sun, the cosmic rays, and when you get in a plane, you're getting up above some of that filtering, and you're getting exposed to more of it. All right, I got a couple people talking to me. Grace first. Yeah, flight attendants, pilots, they have an increase. Now, just because you're a flight attendant does not mean you're automatically going to get cancer. It's just you have an increased likelihood. Okay. Gentry, what was your question? Chiropractors? No. I don't want to get too far off into this, but I do want to say, look into the history of chiropractic. The guy who invented it, I mean, basically, he got the idea from a ghost and then came up with, how to go about it. The American Medical Association calls chiropractic a wacky cult.
My mom's a chiropractor.
I'm just saying.
I'm telling that.
Now, listen, I'm not going to tell you don't go to the chiropractor. I mean, if you feel like it helps you, I mean, it helps you. But as I'm a scientist, as far as the science goes, it doesn't really show any. Now, why is that funny? Why is that funny? I did spend 5 years working in science-related fields. Thank you very much.
It took you 5 years to get your 4-year degree?
No. No, I'm not a doctor. You don't have to get a doctorate to work in science.
I'm joking. I'm not going to tell anyone. My mom owns a flower shop. Are you from
I don't really care either way. I don't believe Miss Erickson has a doctorate. I could be wrong, but
Fruit is.
she's got a master's. I got a master's in education is not terribly hard to get. Okay. How much sun tanning is too much? That's a good question. There's not like a hard and fast thing. From what I've read, about a half hour of sun exposure every day is about as much as you need for your vitamin D, and you should probably limit yourself beyond that. So, yeah, laying outside for 3 hours at a time, probably not so good for you. Well, and here's the thing. Same thing with the flight attendant thing. Just because you sit outside and tan does not mean you're going to get cancer, but it increases the likelihood that you will. No. Because your vitamin D3, the reason why you need some UV is to synthesize the vitamin D. That's kind of a daily thing. You can't like store up 3 days worth and then I don't go outside. Doesn't quite work like that. Yeah, but tanning. The thing is, tanning is actually your body going, quit hitting me with those UV rays. I'm going to put some melanin here to try to keep my cells from dying. I don't know. Yes, getting a tan is your skin sending out a cry for help. Yes. Yep. It's about the same. I think just because it's easier to lay there for longer without getting hot and going, oh, I better go inside, cool off, that kind of thing. I don't think intrinsically. I just think behaviorally how you use them tends to be worse than just being out in the sun.
My cousin one time got a sunburn so bad that it got bubbles on his skin.
You can get second-degree burns from the sun.
If you have a sunburn, don't go in the hot sun.
Okay. All right. Let's talk about visible light just a little bit. So here I've got 3 lasers. Okay. Uh-oh.
Oh, you're going to have to rebuild it.
Okay, I got a green one. I got a purple one. And then a red one. The red one's not working. Wonderful.
You broke it.
There we go. A red one. Okay. Now the thing that we notice about light, and we expect this, our brains are intrinsically set up to expect that light always moves in a straight line. Okay? In some cases it's not true, and that's why we see certain types of things called mirages. So when you see rainbows aren't a mirage. Listen. On a hot day, when you look at like the road and you see that water thing, what you're seeing is actually light that came from the sky. So the light comes down, and because the hot air, the way it works, it actually bends the light, and your brain is set up to go, well, light always travels in a straight line, so if I see that light coming from this angle, it must be down there where the road is. But because it started off from the sky, it gives us this weird illusion. The other example is when you take, I should add a glass of water here, but like when you take something and you put it so that it's in half in water and half out, again, your brain thinks that light moves in a straight line, and so the light that goes through the air does move basically in a straight line. The light that comes from the water actually bends a little bit when it comes out, and so your brain goes, oh, well, this part of the pencil must be over there, and it looks like it's broken.
Yeah, like Scooby-Doo.
I can't hardly hear you, sorry. Yeah, so those mirages that they see in deserts, that again is the sky being bent down. Now, it sort of looks like water because, of course, the sky is blue, and so it looks like this shimmery water.
Explain the trees, the palm trees.
That could just be like heat exhaustion, that kind of thing. You usually don't see trees, no.
No, you see palm trees.
Okay. What's that? A rainbow is not really a mirage. There, the light's being split into the different colors, so it's a little bit different case. The light that comes from the sun. All right, listen. For a rainbow, the light that comes from the sun gets split up by the water droplets. It gets split into its different colors. I mean, it's sort of like a mirage in the fact that the thing, there isn't something that's actually there, but it's just light that's being split up instead of just being bent. It's a slightly different occurrence. All right, so the reason why we don't see the beam is because the beam of a laser shoots in a straight line. That's the whole point of a laser. Unlike a flashlight where the light spreads out, this moves in a straight line. If it doesn't bounce off anything, you're not going to see it. Listen. To see light, it has to bounce off of something. Now, one thing that we can do is we can put something in the way.
Have that glass tube.
No, not that. Where'd I put that baby powder? Oh, over here.
Is that made for real or artificial beams?
Real babies always.
Obvious. Whoa! Wait, do it again. I bet the floor's gonna be slippery right there.
Okay, so if we put dust in the air, then there are
Do it again.
are things that it
Is that why in
doesn't work very well.
movies when they when there's like
Okay, where's the purple one?
spy movies they'll sprinkle something?
Right. And I'll tell you in a minute why that's kind of stupid.
It smells like an 80s. Look at that. Oh, wow. I hate babies.
Right. So listen, Grace is absolutely right. It does the exact same effect as when you see light coming through the windows and you see all those little dust particles. There's something that the light can bounce off. So in this case, because there's things in the way,
We can't buy kids.
there's something for the light to bounce off of.
Sure, we gotta get through the laser beam. It's like Spy Kids.
Uh-huh. So here's the reason why those movies are kind of stupid. Sorry.
I feel like, look at the table. Wow.
All right, listen up here.
Oh, I'm choking on the
I'm like LeBron James.
Hey. All right, listen. So those movies where the spies take the stuff and spray it, yeah, that would work, except that's stupid because absolutely nobody would use visible light beams as their security system. You can do the exact same thing with microwaves or infrared, and they wouldn't be visible, so people wouldn't be able to spray anything and be able to see it. So nobody uses visible light beams in that type of security system. Here's an example. We have those types of things that we use on garage doors to keep them from closing on things, right? You don't see a beam because it isn't visible light. I'm not actually sure what wavelength they're working in there. I think it's infrared, right? If you sprinkle what? Yeah, sprinkling baby powder won't do anything because it's infrared. Your eyes can't see it anyway. Okay? Here's something that's cool, though. This thing right here shoots an infrared beam to the projector to communicate with it. Okay? We don't see it, of course. We don't see a beam or anything like that because it's infrared. If this shot visible light, then every time I push this, we could put some stuff in the way and we'd see it just like a laser light. But your cell phones, at least some types of cell phones, the cameras on them will pick up a little bit into the infrared. So here's what I want you to do. Take out your cell phones, put it on the camera.
No.
What?
So your TV remote?
Yeah. Yes. That's why it won't go through glass.
Okay, long cameras. Yeah, that's why you can put stuff in front of the
Right.
dish box.
Now, just the camera app. Good Lord. So, first look just up here with your eyes. Okay, I'm going to press. I don't know what button I should hold down. Maybe just freeze. Okay, you can't see anything, right? Now try to look through the camera, and certain types of cameras should be able to pick up kind of a flash.
No, I don't see it.
Right here.
That or your face. Should I zoom out?
Right on where the emitter is.
Oh, do I gotta zoom in?
I took it out.
Try it again, Mr. Roark.
It's not working.
No, you didn't.
Everybody? I want to say iPhones don't have the right. I think you kind of have to have a.
Look at my iPad.
Still in after.
Here, let's try this.
See your phone and do it right.
Okay, do it again. Do it again.
So let me do this.
Mr. Roark,
Okay.
no.
So we can't see anything lighting up there with our normal eyes, right?
Nope.
Okay.
I can't see that.
Let's see here. Isn't that cool? So what's happening is, and for whatever, I don't know if it's. Good Lord.
There we go.
I don't know if it's the camera hardware or if it's the software
You did not.
that is the difference between iPhones and these. Okay, just a minute. Let me explain it first, and then I'll do it again. Okay? But on my phone, what is happening is
Shut up, Isaac.
the camera, unlike our eyes, is able to detect the wavelengths that are given off by this remote. Okay? But then the camera is going to take that information and put it, for us to be able to see it on the screen, is going to put it in a visible light medium. And so it converts it up a little bit so that we're able to see it. Because it's like, oh, I'm getting data here. We need to make it so that human eyes can see it. So I don't know why there's a difference between the iPhones. That's something I guess I could look into.
At all the people that I
What's that?
saying that they saw it.
I don't know.
Try it again. Liars.
Nothing?
Nothing. iPhone. You lied.
Okay. Sorry. Woo! That's just the. So. I'm not sure why it would be purple, actually. That's.
How far will it reach? Because it's cold Vikings.
Here, let's try it. Let's try it with. With more of the light off, so it's not being washed out. I was looking around for the remote. Uh-oh. Where's the menu?
Roark, I got a slow-mo of you. I'm not joking. Oh, time-lapse before. I see a light up there. Allahu Akbar. Oh my frick.
Yeah, I mean it diffuses pretty quick.
Oh, I see it. Oh my goodness, look at that. Oh my God. I only see your phone. If you move your phone one time, I think we might get it. Oh wow.
I don't know. Anyway. So what, everybody's got an iPhone?
Let me try with the flash.
Bunch of communists. There's nobody in here that's got an Android? I just did. Well, the thing I don't like about Apple is they're like, you're going to use our products in the way that we want you to. And you're like, well, but can't I just put like some icons down here and a few up here? No, you got to have them all together.
What do you mean? You mean like rearrange your...
Yeah, but like when you rearrange your icons, right, it just puts them all, like on an Android, I've got one page that just has like my emails on it. That's it. And I've got another page.
How many emails do you have?
Can't
The thing
show
is,
me.
most people don't care, so they just, like...
Well, most of you guys don't care because you're communists.
I could care less. Why does that make me a communist? I just don't care.
I don't know. It's because it's funny.
Don't you ever call me a communist.
All right, we already talked about that.
I'll tell my mom on you. Mr. Roark called me a communist.
Roark, we don't have time.
All right, let's talk about this. Oh, yes, we have time. Oh, yes, we have time. Now, we will actually do this tomorrow, but I want to introduce it first. What's cool is if you take a gas, right, and you send electricity through it, it's going to glow. And I'll show that to you. We'll actually pull the tubes out and do it tomorrow. Okay? But if you take any gas and you send electricity through it, it will actually glow. So like helium or oxygen, I forget the tubes that we have. I'm pretty sure we have hydrogen. I know we have neon. Okay? And that's how neon signs work. So in a neon sign, they have basically just a glass tube that's filled with a gas. When it's off, nothing's happening. When you turn electricity on, that gas glows. And it will glow a specific color based on the gas that's in there. Now, we say neon signs, but neon actually only glows red. If you see... I love it. I love it when I just say a fact and people are like, what? That doesn't make any sense. Neon only glows red, okay? If you see other colors in a sign, those are other gases or maybe even mixtures of gases. Green, I think argon.
How does that explain my neon?
Okay, now listen. Shh.
Yeah, we're going neon green.
Tiny little bit.
Class teaches me is that the world is lied to me.
Yes. That's what I'm trying to show to you, yes. That as well. So, listen. We will get the tubes out tomorrow and we'll see, okay, different colors when we send electricity through it. What's awesome is we will have spectrometers that we will look through that will actually do the same thing as a raindrop and split the colors up.
Where are you going to get a...
Chemistry used to be a fun class to teach. Now, when you look at a rainbow, what you see is a whole breadth of colors because the light that comes from the sun is made up of all different wavelengths of visible light. But from the gas tubes, there are only a few different wavelengths. This right here is called an emission spectra. Okay? This is... No! Can we please be quiet and listen so that we can learn about emission spectra? So, if we look at a certain element, what we will see, or a certain gas, what we will see when we look through a spectroscope that splits it up into colors is we will see bars at certain places. Okay? So the color that comes off is a mixture of these specific wavelengths. This is what we would see if we looked at light from the sun or from a light like this. All the colors. Okay? But from that specific gas that we're looking at, we would just see specific bars for the wavelengths of light that are produced. So what that tells us is that from the light that comes out of those gases, there are only little, specific wavelengths, only certain wavelengths that are coming out. Okay, question.
What about people that are colorblind?
Well, yeah, there's red, green color blindness. That doesn't change the fact that different wavelengths of light are coming out.
Like everything, every color we look at is a different color. Not this year, but this isn't actually pink because our eyes pick it.
Well, I think what you're thinking about is.
Every color but pink or whatever.
Isn't it that we have 3 different colors in our eyes and some of them overlap?
There is that, yes. So what Chloe brought up is that when we say something is red, right? When we say Haley's shirt is red.
Haley's hair is red. It's everything.
Well, I don't love that description. It just means it's absorbing all the colors except red. But what we see is the light that bounces off. So, yeah, you can sort of, it seems all mind trippy. I'm sure if you do it, well, you think about it when you're on shrooms, it'll seem like a huge breakthrough. But, honestly, that's how we see everything. When we see stuff, it's because light bounces off of it. So, I guess you could think of it, it's every color except, but that doesn't really make any sense. It just means it's absorbing every color. What we see is the reflected color. So I would still say, well, the shirt is red because it's reflecting red. Okay? No. Listen. The other thing is that Bryson brought up, yes, we only have 3 cones in our eyes. Okay? We've got cones, well, there are rods that the rods do light and dark. The cones are the color. Shh. And those get stimulated by certain wavelengths. Okay? One type of cone gets stimulated really well when red light hits it. Shh. It will also get stimulated a little bit. It'll also get stimulated a little bit when purple light hits it, but so does the blue cone. And so when we see purple, that's because red and blue cones are both being stimulated by that wavelength of light. So for most colors. There is a specific color wavelength. We see that up here. But like I said before, there is no pink light. When you see pink, and we'll watch a video on this later, when you see pink, our brain is interpreting, hey, these cones are all firing, and we're going to, our brain says, oh, we're going to call that a different color. I mean, and then, facets of that, fuchsia, and whatever. Kind of, yeah. Yeah, well, yeah, so brown, there's no brown light either, but brown is more of a mixture of all the things. That's a good point. White is all of them, all the wavelengths, and black is none of them. I'm not sure the specific cones that are involved, but it would just be how those are being stimulated. Okay? So, the thing we need to realize is that for each gas, the emission spectra that's given off is different, which means this is a fingerprint. If I shine neon, I electrocute neon gas and light comes out, and you look through it through a spectrometer, you get a specific emission spectra, specific lines that are, will only show up if that specific gas is stimulated. Okay? Yeah, tomorrow I said. Okay? We will do it tomorrow. We just don't have time to get it today. I'm trying to introduce it. Okay? So, what this helps us do, I mean, we've heard, hey, the sun is made out of hydrogen. How do we know that? Well, we can take hydrogen and stick it in a tube and look at it through a spectrometer and see the lines. And then when we look at the sun, we see, hey, it glows more brightly at these places than it does at all the other ones. And so that tells us that there's some hydrogen there's hydrogen in the sun. Okay? Helium was actually discovered through a spectrometer in the sun before we ever knew that it was here on Earth. In fact, helium comes from the Greek word helios, which means the sun. It was named after that because that's where it was discovered. So a scientist was looking through a spectrometer. He's like, hey, there's this emission spectra, this fingerprint, that doesn't fit any other element that we've ever seen before. Must be a brand new element. Let's call it helium after Helios for the sun. And so they named it, and then later they discovered, when we find these places where there's oil underground, there tends to be helium trapped up at the top of the caves, and we can take that out and put it in balloons and talk funny. But it was actually discovered in the sun before we ever knew about its presence here on Earth. Okay? Now, another thing that we can see is what's called an absorbance spectra. If I take that same gas and I shoot white light through it, I don't electrify the gas, I just let light pass through it, it will actually absorb, the wavelengths of light that get absorbed will be at the exact same frequencies as the light that's emitted. So when we shine white light through, we can see an absorbance spectra, and that tells us that that element is there. Scientists use this to actually look at planets outside our solar system and tell what types of gases are in the atmosphere. By the light that comes from their stars, when it goes through the atmosphere of the planet, some of those wavelengths will get absorbed. There will be holes in the light that comes out, right? It won't be a full rainbow like this. And we can go, I see missing lines here. That corresponds to the emission spectra for hydrogen. There must be hydrogen there. Or oxygen. There must be oxygen there. And so we can use that and look and go, hey, this planet has a lot of oxygen. From what we know, that kind of signifies there might be life there because this planet didn't have any oxygen really in its atmosphere until life showed up. Mars does not, no. Not right now. It's still possible there could have been life on Mars. Right, and Mars's gravity is so small that it doesn't hang on to its atmosphere very well, so if it happened a billion years ago, any of that oxygen would have floated away already. Well, yeah, incorporated in there, but we're talking about elemental oxygen in the atmosphere. Well, it doesn't. Listen. Here's the helium thing, then we'll be done. Real quick. When you inhale helium, your lungs expand and your brain goes, oh, I took a breath. Okay? Even though you haven't pulled in any oxygen. And then you talk funny and breathe out, whatever. During that whole time, for your body, it's just like you held your breath. That's all. The reason why it's dangerous is because people are stupid and they go, they talk funny, and then they immediately take another inhale of helium. Well, the whole time you're doing that, it's like you're holding your breath. And yeah, your brain's going to start to die if it doesn't get enough oxygen. So, helium is a noble gas. It doesn't react with stuff. It doesn't kill brain cells. What kills brain cells is holding your breath forever. So what you want to do if you're going to talk funny is take breaths in between. Okay?
Why does it make your voice like that?
It's just because of how the sound vibrates in the air column.
No question of the day.
No question of the day.
Well, what happens